Welcome to the video write-up of the Cookbook challenge from the bostonkey.party CTF 2016. I actually solved this challenge during the CTF this time, so it's not a video write-up based on write-ups from other people, and I've tweeted about it because I spent 24 hours or so on this challenge, which was a little bit over my skill, but I learned a lot along the way, and so I'm gonna show you now how I did it. The Cookbook challenge gave 6 points, which was 1 point more than the other Pwnable that were released at the same time. And it says that the Top Chef wrote this cookbook for me, but I think it has an extra secret recipe. And it was provided a target set and the server and port for this running service, which you could connect to during the CTF and interact with the service to exploit and gain remote code execution. When we unpack the target set, we find the Cookbook binary, which is a 32-bit Linux binary. So that is pretty cool because then I can actually use my IDA license, which only has 32-bit. And we get a libc, which is an indication that the binary uses ASLR, or at least the system has ASLR enabled, because we then need this when we leak addresses of libc to calculate offsets of different functions and stuff like that. So that is a good indication on what we will face. I use Vagrant as a virtual box wrapper, so I now connect to my Linux machine, to my Linux VM running in VirtualBox, and I copy the target set into the shared folder so I can access the files in my Linux system. So this is at the moment the Linux VM running. I connected to it with SSH. So unpacking it and ready to go. So let's have a first look at it. When we execute it, it asks for our name and it has this cool ASCII cook, and then there's this menu where you can type in certain letters to navigate the menu, and you can list ingredients and look at recipes. You can, as you can see, you can add ingredients, you can create a new recipe, you can discard the recipe you're working on right now, you can save it, you can print it, and so forth. So there's a fairly complex menu where you can interact with it. You can, for example, I just added an ingredient to a recipe and hex 41 of that ingredient. So I add another ingredient like water, hex 40 of it, and then I can list the ingredients that are in this current recipe. So that's the functionality basically of this program. Just to get a feeling for it and not to overlook something, just play around with it a little bit, and so you get a mental picture of the functionality of the program. There's also a functionality to name your cookbook, where you have to specify the length of how long the name of the cookbook should be, and then you can enter the name for it. And here I show you an error that will occur, which you might find while just playing around with it, but maybe you don't, which you could also easily fuss if you just random stuff against it. So now we remove the cookbook name, and if you remove it again, just trigger R again, we get this error, a double free or corruption or top, which is indicating that there is a double free with the heap. It's basically very clear. So this is something you could find during initial investigation. I personally didn't. I started reverse engineering it in IDA and then realized those issues, but it's clearly something you could find also with just throwing randomly the menu items against and just fuzz it. So now I've loaded the binary in IDA and I start reverse engineering it. So, but where to start? So the first thing I do is I look at the strings embedded in the binary, because we know there's this string cat menu. And if we look at what the start of the program basically is, we can figure out and start tracing the execution in IDA from the start. So the first string when we execute the cookbook is what's your name. So this is also what we want to look for in IDA. But what I also do is I start taking notes of the functionality and certain stuff of the behavior, which is important because it's a fairly complex menu with a lot of functionality. And so you want to know which menu item is responsible for a certain behavior. So I write down now that the first thing that we get is what's your name. And then after that, we get access to the menu. And then let's explore the menu. So L just lists the ingredients, R prints the receipt book, but add ingredient provides us another sub menu for adding a new ingredient. So I'm just taking notes of this fact that when we get add ingredient, we enter a different menu. So I'm cycling through the other things, and if we type C, we create a recipe, which is another sub menu. So I also just take notes of that. Well, yeah, and otherwise, there are some more functionality, but it's not really a submenu. So for now, I just, leave it at that. Now let's find this string in IDA. What's your name? There it is. So then we can look for the cross references, what is referencing the string, and we find this one function here, which seems to print this this question, and then you can also see it does it allocates 40 hex bytes, and then afterwards it does an fget, so it's reading your name into the allocated 40 hex big area. And this function is called from this other function here, which looks like maybe the main function, because there's an indication that they use alarm, which is very typical for CTF challenges, because they will create an alarm, which is basically just like a timeout they wait for in case the binary hangs, they can kill it, which is typical for CTF challenges, that they don't have a lot of hanging processes. So we can also look at the next function, and that is called afterwards, which looks like printing some ASCII stuff, and in fact it's printing this cook here, as you can see here. So this is definitely the function that will print the cook. What is the next function in this list? So this function just calls two different functions. Let's have a look at the first one. There seems to be some names like onion and water. That looks like the initial ingredients that are already in the binary in the menu, or that are already available if you list them. So this is probably initializing the ingredients for this binary. Those are just names you come up with now. Maybe later you realize the function is doing something else, but for now this is what I think it's doing. And then it calls for each of these ingredients and calling another function. So this might be a function that adds an ingredient to something. I already reverse engineered, so I know that there is a list of ingredients, obviously, where kind of like an array, but it's not a real array. It has its own structure. So I know that it has to do with adding this ingredient to the list. But yeah, the next function after we initialize those ingredients looks a bit more convoluted, a bit more. It looks different, but it also has those strings in there. And if you look at those strings closely, and if you think about what else was already initialized at the start, which was those basic receipts that were already in the binary. So this is probably just initializing the recipes available at the start of the program. So that is init the recipe. And this all is then just initializing the cookbook. Okay, what's the next function? That looks familiar. That seems to be the main menu with all our options available. And there's this huge jump table where, depending on the input, we will execute different things. So we can just start going through them one by one and start understanding what they are doing. After you read fgets value, this is one of the options you can choose. So it looks like a loop. It's looping from the bottom to the top again. So it seems like cycling over something. You can also see the dashes, and you might be able already to guess what it is, but maybe we don't know for sure. So what I'm doing now is the next step of kind of also dynamically analyzing this. I take the address of this function and I set a breakpoint. And I just run this program, and then I just hope I find the menu item that triggers this breakpoint. Playing around with it a little bit, and there we hit the breakpoint. So this is obviously the last action I did was I was listing the ingredients available. So that lists the ingredients. And this ingredient list has to start from somewhere, and there is this global variable in the data segment, and this is a special segment because even though we use ASLR, this is like a global variable and will have a fixed value, which is loaded from this address here. So it loads the first one, whatever is there, and moves it into a local variable. And we can see that it's then doing stuff on it. And again, I looked at it more closely, but this is something you would figure out when you step through it, that it's cycling in a certain way over this starting from the first pointer you have there. And you can now name this global variable the ingredient list. So let's get to the next function. So there's a string, the %s cookbook, and if you print R, we know that this is the current receipt book that we can print. So we can name this function now and then proceed to the next one. The next one seems to start another menu, and if you look at the strings, this seems to be the add ingredient submenu. As you can see in this function, it will print the options in the menu, and then again there's this huge jump table. You can see this very nicely on the graph overview on the left in IDA, that you have all those different options. And it looks a little bit more complex than the main menu, but anyway, it's very similar. So let's move to the next function. The next function again seems to specify a new menu, and we know that this must be then the add recipe menu. The next function, it says how long is the name of your cookbook. So that seems to be the functionality to give your cookbook a name, because that is asking for the length of the name. And we can move on to the next function. So this one just seems to take another global pointer from the data segment and then free it. So there seems to be a menu item that just takes it and then frees something. So let's make a breakpoint here again in IDA and see which menu action triggers this breakpoint. We can try a few things. And eventually, if we press R, so remove the name of the cookbook, it will trigger the breakpoint. So this is the remove cookbook name. Then this global pointer here must be the cookbook name. And if you closely there, it doesn't set this cookbook name now to 0, and that is why we get this double free error if we press capital R 2 times, because it tries to free the same memory again without having any checks in place. And if we look at the give cookbook name now, we can see that there's a call to malloc with the size that we previously entered with fgets, and then the pointer returned by malloc, which is the area where the cookbook name will be stored in this global variable cookbook name. Then let's move on with the next function. So here you can see the goodbye, thanks for cooking with us. So that seems to be quitting, the quit message. And then here is the which ingredient to exterminate. So this seems to be the location that we'll jump to when we want to remove an ingredient. And when we want to remove an ingredient, it seems to call this other function here. When we look into it, it looks fairly complex and seems to do a lot of stuff. So for now, I put this aside and I don't want to reverse engineer that one. But we can guess that this might be the function because there's a free afterwards. It might try to find the ingredient that you want to exterminate and remove and free it. So maybe that is what it's doing. So let's note this down. Now that we are done with the main menu, we can move into one of the submenus. The first entry of this submenu seems to malloc something. So let's set a breakpoint at this address and see which actually menu item it is. First I thought I was in the add ingredient submenu and I was confused that nothing of it will trigger it. So I looked again around to verify in which submenu I'm currently in. So I gotta quit out of the add ingredient menu and get into the create recipe menu. From there I can type N for a new recipe which will trigger the breakpoint. So apparently this malloc here will allocate a new recipe on the heap. And we can see that it callocs or mallocs or whatever hex 40C bytes on the heap. So we can take notes of this now that this particular menu item will malloc this size on the heap. And the result of this calloc will be stored at another global variable, which in this case must be the current recipe we are editing. We are creating a new recipe, it's allocating it, and then storing that address in a global variable. And the next menu item, which seems to free that area, we can verify this by, D, which seems to discard the recipe and triggering it 2 times, will create a double free error on the heap, because we are trying to free the same location twice because it doesn't get set back to 0. So we know that the discard recipe menu item will free the global variable current recipe, which was earlier set from the malloc. And we can now fill in also the other stuff that I kind of forgot in the beginning. When we give your cookbook a name, we can specify a length X, and then it will allocate or malloc the cookbook name with this size. And remove cookbook name will free this global pointer again, which is again a double free because it does not reset the cookbook name. We can look around a little bit more, and the next block seems to be the add ingredient functionality in recipe, but it's maybe not that important right now, and maybe we move on to the add ingredient submenu. The add ingredient submenu again is very similar. You have the printed menu and then the big jump table. So the first entry also moves a global variable in EAX and checks if it's null or not, and then either will do something with it, call something, or print null. And this global variable is again used quite often. So we can already make this assumption that this is probably the current ingredient we are editing, because the first item in the menu is also list ingredient. So, or print a list current stats, basically printing the current ingredient. So probably the first function here, if we also look at the strings in it with name, calorie, and price, is exactly what this menu item does. So this will print the current ingredient, and based on the current ingredient pointer, global pointer that is set. And so this must be the new ingredient functionality, because it does malloc, and the result of malloc will be moved into this global address. When we move a little bit further, we can also find a free, which is taking this global pointer again and then is freeing it. But this free is much more interesting, because as you see, this submenu generally checks if current ingredient is 0 or not, and then printing can't do it with null. And the free will also, after the free, it will set the global pointer to 0, and thus preventing us from double freeing it. Then there are more menus. You can look just at the strings that are using it, and if you are unsure which part is which menu item, you can always set a breakpoint and then just check out the recipe and see which functionality it might be. And give the name to the ingredient with G will trigger the breakpoint, and you can also see in the information where the breakpoint was hit that there is an alloc. So this seems to allocate the buffer for the name for a particular ingredient. And then that one is stored in a local variable for now, the location of the string, or the allocated area. And if there is a current ingredient be edited, then we will do an fgets and read it into the the address of the local variable. So it will read into the stack at this allocated area, and then it will move then it will mem copy this string that was read in to the location of the current edited ingredient, but not at direct the start. It will add EAX 8 on it, so it will move the current ingredient address 8 bytes ahead, and then mem copy the string that was read at this location. Maybe we can also have a look at this in GDB now, because we know that this is a global variable which will always have the same address, so we can just look at it, what kind of value it will have. So we already have created a new ingredient, so there should be actually a value stored. So this seems to be an address where the current ingredient is, and then we can print this, and yeah, it looks null, it doesn't seem to be much there. But as you remember, we just started to write a name to it. So if we continue and type something in, that will be the name of the ingredient. And when we look at it now, we can see that at offset +8, so that is +0, next one is +4, and that is +8. At this location, we will store the string that was read. And remember that reading the string we first read into a newly allocated buffer. That's why the name is there doubled. If we take a look again at the giving it a name function, we see that after the memcopy, we copied it, we will free the area that was previously allocated. And this one FCC1 is the so-called wilderness. That is the last value on the heap, which indicates how much free space is there on the heap. So everything that comes after that value right now is freed heap, and free doesn't set magically the memory to 0. So obviously you can still find the strings that were previously stored at this area, but it's not used by the application anymore. So let's look around and maybe, start working through the other stuff. I'm looking for one particular function I want to have a look at. And again, if you look at this and you don't know what it is, you can take the address and create a breakpoint in GDB for it and see which menu function will trigger it. If we set a price for a current ingredient, it will not trigger it. But if we set some calories with S, then we will trigger it. And we can have a look at it. It first allocates a new area, and we know that this is now set calories. And then it checks if the current ingredient is 0 or not. So if we have currently an ingredient. And if we have one, it will call A to I on the string that we read, which will convert it to an integer. And then the result is coming from EAX, that is the return value stored in this local variable var20, which we can now rename to the calories integer that we have read from standard in. And then it also takes the current ingredient address, EAX, and then it stores at the location of this ingredient, it will store the calories. So remember, the string was stored at offset +8, but the S, the calories for an ingredient seems to be stored at offset 0. And we can verify this by just specifying a number and have a look at it. So I will now give this current ingredient the calorie count of 1, and I will give it the price of 2. And then we should, if we look at the ingredient in memory, we should see exactly 1 and 2 in the first thing. Also note that the string is gone in a second because I accidentally screwed some stuff up. This is a new ingredient that I added, which I didn't specify a name at this point. But as you can see, the calorie count is stored at exactly the address of the current ingredient. The price is stored at the offset +4, it's the second value. And after that, at +8, you will have the string, the name of the ingredient. And we can take notes of this again in our notepad. So the price ingredient will write at the current ingredient plus, and that's actually wrong, it should have been +4. It will write the integer that we can read and set calories at 4. So I actually mixed this up, but you get the idea. So basically, this is how the reverse engineering works and what I did. And obviously I did a lot more because I spent a lot of hours, as you know, on it. So you just work through the IDA and understand function by function. Maybe you start to get the ideas. Obviously that you can free memory and still write to it and still free it again and stuff like that. You know that there must be bugs that you could abuse. So what I'm doing now is I show my exploit, and then we will see in part 2 of this video a walkthrough of my actual exploit in the end. And I use SoCut now to simulate the service. It will open a TCP port on port 6066, and when I connect to it, it will execute the cookbook, and I can interact with it like it was with the live challenge. Now I will open my exploit because I have to do a slight modification with the server and port. And then we can also use netcat ourselves to see if it's working. So netcat connecting to 127 to localhost. I'm currently on the Linux machine also, that's why it's localhost. And then it presents us with the name and the menu. So this is how we can interact with the binary. And it's like the service, like the CTF challenge was when it was live. And you can see now if we trigger the double free, we can also see the error on the SoCat server side. But the service you are looking at is just, dying. Now let me show you my exploit first, and then in the next part we will have a look at it more closely. So there are multiple steps to this exploit, as you can see, and I paused it every time you have to press enter to continue, and it looks very complicated, but we will have a look at it. And in the end, you are presented with a shell where you can execute shell commands, and it works nicely. You can see that my exploit looks fairly complicated. There seem to be a lot of steps involved, and I've seen write-ups already or proof of concept codes from other people on IRC that were simpler than what I did, but I'm proud of it myself. I did it myself and I'm very proud of it, and in the next video we will step through the exploit and look at it, what is actually happening. Here's also the output of the live server when I got the flag, and you can see here the user it's running with, and here the flag itself. Hey, my girl does work here. And if you remember my Twitter message from the beginning, what it did was I had this SHA-1 hash in there, which was generated by concatenating LiveOverflow dash with the flag. So just basically as a proof that I got the flag and solved the challenge before the end, and this time I did not just work through write-ups from other people, I solved it myself, which makes me very happy. So when you debug the binary in GDB, then GDB will basically disable ASLR for this binary, and all the addresses will be static. And in the end, your exploit has to work with the ASLR on the system enabled anyway, and also write your exploit to interact with the remote service. So what I do is show you now how I can deal with it. So I start the exploit and it's now waiting at a certain address, and basically now I can use can look in the processes and see that Cookbook is running, and I can get the process ID from it. And then I can use GDB to attach to this process ID. So GDB -- PID equals to, and then the PID of Cookbook, and then I can attach to this process, and then I can start setting breakpoints, investigate the memory with the exploit running. And this is basically how I developed then my exploit. I always written a little part interacting with the process, set breakpoints, investigate memory, and so forth. See you in part 2 to analyze my exploit step by step.